Determine if the system of linear equations is inconsistent or dependent. If dependent, find the complete solution. First, we obtain an augmented matrix for the system of equations of 4 variables, but there are only 3 equations. The first equation is 1x minus 1y, 0z, and 1w equals 0. The second equation is 3x, 0y, negative 1z, 2w equals 0. The third equation is 1x, negative 4y, 1z, 2w equals 0. First, we will turn the entry 3 in the second row to 0 by taking row 1 multiply negative 3 and add to row 2 to obtain the new row 2. If we take row 1 and multiply negative 3, we'll get negative 3 times 1 is negative 3, negative 3 times negative 1 is positive 3, negative 3 times 0 is 0, negative 3 times 1 is negative 3, and negative 3 times 0 is 0. And row 2 is 3, 0, negative 1, 2, 0. Adding the two column wise, we'll get 0, 3, negative 1, negative 1, 0. And this will go to row 2. To save a step, we can also take row 1 multiply negative 1 and add to row 3 to obtain the new row 3. The negative of row 1 is negative 1, 1, 0, negative 1, 0, and row 3 is 1, negative 4, 1, 2, 0. Adding the two column wise, we'll get 0, negative 3, 1, 1, 0. We now have an equivalent matrix. We keep the first row, which is 1, negative 1, 0, 1, 0. The second row is now 0, 3, negative 1, negative 1, 0. And the third row is 0, negative 3, 1, 1, 0. Observe that the second row is almost identical to the third row. If we take row 2 and add to row 3, we'll obtain an equivalent matrix 1, negative 1, 0, 1, 0, 0, 3, negative 1, negative 1, 0, 0, 0, 0, 0, 0. The third row or the last row in the matrix states that 0x plus 0y plus 0z plus 0w equals 0. The second equation states that 0x plus 3y minus z minus w equals 0. And the first equation states that this is 1x minus y plus 0z plus 1w equals 0. From the last equation, we will read this off from the diagonal only. From the last equation, it states that 0z plus 0w equals 0. And so regardless of what z and w is, this statement is always true. The z and w can be any real numbers, so we let w be t and z be s. These are the two distinct real numbers. Then from the second equation, we have 3y minus z, but z is now s, minus w, but w is now t. Isolate y, we have 3y equals s plus t, so that y is s plus t over 3. From the first equation, we have x minus y, but y is now s plus t over 3, plus 0z plus w, but w is now t. We have x equals s plus t over 3 minus t. The common denominator is 3, so this is s plus t minus 3t, or simply s minus 2t over 3. We obtain a system that is dependent with two parameters s and t. The complete solution is x equals s over 3 minus 2t over 3, or simply 1/3 s minus 2/3 t. Y equals 1 over 3s plus 1 over 3t. Z equals s and w equals t. This is the complete solution where s and t can be any real numbers, and that the system is dependent. There are infinitely many solutions here.